Thank you for coming along. Seccomp. I've got a lot to cover, so I'm going to go real fast. I think I will say, I'll take questions as I go. If I get too many questions, I'll say take them to the end. But for the moment, I'll say I'll take questions as I go. Some of you might have already attended Martin. I won't try and pronounce Martin's surname. The presentation on Seccomp today. There will be a bit of commonality with what Martin covered, but Martin was taking a much more practical approach than I'm going to take. I'm going to be sort of, this is the theory, or this is the details. Okay, what do I say? I did stuff with Linux. I do stuff with Linux. I do training. I like Oslo. I will do training in Oslo or elsewhere. So, bit of a quick introduction. What's the idea here? The kernel provides system calls. System calls are the way that programs ask the kernel to do things. In the Linux kernel, there's about 400 system calls. The way a lot of us think about system calls is they're a way of getting the kernel to do something for me. The way an attacker thinks about a system call is, hey, this is one more way in which I can try and attack the system. And oh goody, there's about 400 of them, and let's try them all out. But most programs only use a small subset of the available system calls. Even a big program like Emacs probably only uses 10% of those 400 different system calls. And most of the other system calls, they don't get used. So the supposition is that suppose you've got some program and it makes a certain set of system calls, and one day you observe it makes another system call, different than you ever expected. Perhaps the reason is the code got taken over by an attacker, got compromised by an attacker, and the attacker is making the program execute some arbitrary code, the process execute some arbitrary code in the hope of compromising the system. So if you see the program make an unexpected system call, then you want to stop that from happening. And this is what Seccomp lets you do. It lets you prevent the program making unexpected system calls. And the idea then is, of course, that you're removing those other possible vectors for attack because the attacker can't exercise those other system calls that were not expected. We're reducing the attack surface of the kernel. The whole point of Seccomp then is a fundamental building block in various kinds of sandboxing tools and in container frameworks and so on. Seccomp's been around for quite a long time, but at the beginning, back in 2005, it was a much simpler thing. It only really became interesting in 2012, so just over 10 years ago, when the functionality got greatly expanded. And this is such a change that occurred at that time that you see some people talking about Seccomp 2, because it was such a major change from the original Seccomp. And the key thing that happened in Seccomp 2 was that you were able to choose which system calls were allowed and disallowed. In the very early version of Seccomp, there was a fixed set of system calls that were allowed and everything else was disallowed. But Seccomp 2 in version Linux 3.5, 2012, things became much more flexible. People had wanted this. I've got to change my device there. The battery must be getting a bit flat. People had wanted this feature for a long time. There'd been, well before 2012, there'd been attempts to merge this sort of functionality in the kernel, but they'd all sort of, for various reasons, failed. But once Seccomp got merged into the kernel, sort of the floodgates opened, and many people who wanted this functionality then started integrating the functionality into their applications. So this is some examples of some well-known applications that use Seccomp. Web browsers use it, sandboxing the renderer process, for example. The container frameworks use it. Even strace uses Seccomp to do a quite clever thing to speed up certain kinds of system call tracing, which seems a little bit surprising, but if you go away and read about what strace is doing, it actually uses Seccomp to actually speed up certain kinds of system call tracing. A bit more history. In 2014, a new system call was added. There was an earlier system call called PRCTL, which was used for implementing Seccomp functionality, but in 2014, they added a dedicated system call, which provides all the Seccomp functionality that PRCTL had, but adds some new stuff as well. And this is really the system call of choice going forward. Seccomp's a lively area of development in the kernel. There's really quite steadily new stuff being added all the time in terms of new pieces of functionality for Seccomp. So it's this a lot of stuff keeps happening. So the fundamental idea of Seccomp, you can do filtering, limitation of which system calls are allowed. The limitation that you can implement is based on the system call number, in other words, essentially the system call name, if you like, but except the kernel doesn't know about names, it just knows about numbers, and system call arguments. And what I mean by that is the values in the registers. This was something that Martin pointed out this morning as well, that the registers that contain the arguments might contain pointers, but you can't dereference those pointers to find out what they point to. You can't make decisions based on what the pointers point to. That's a little unfortunate, but there are good technical reasons for that and good reasons around security for that. But for instance, if you had an argument that was a pointer to a path name, you might say, well, I want to make a decision based on what the path name is in my Seccomp filter. You can't do that sort of thing. The general idea, we've got sort of 3 steps in the operation of Seccomp. The first thing we do is we construct a filter program. This is a program that's going to make decisions about what system calls are going to be allowed and disallowed. So we build that filter program. We load it into the kernel, and when I say we, I mean a process loads for itself a filter into the kernel, and this is done using either the Seccomp system call or the PRCTL system call, and after that we execute some code that we somehow don't trust. Perhaps we're about to exec an untrusted program, or we've dynamically loaded some shared library. We're going to call a function out of that shared library, some sort of plugin functionality, in other words. And for some reason, we don't trust the code that we're about to execute. Perhaps we're worried it could be compromised. Perhaps we even think it could be possibly somehow malicious. And after we've done this, from now on, every system call that the process makes triggers the execution of the filter, and the filter makes the decision, is this system call going to be allowed or disallowed? And if the system call is disallowed, the kind of disallowing, there's a few different choices that we can make here. The filter might say, well, don't execute the system call, but make it look like it failed. Or maybe the filter says, actually, we really don't like this system call, kill the process. There's a few choices. Once we've installed the filter for the program, this is irreversible. When we install a filter, we're essentially making a declaration. We're about to execute some code we don't trust. And we certainly don't want that code to be able to remove the restrictions. The The filters themselves, they're expressed using a language called BPF, Berkeley Packet Filter Syntax. This language, essentially, it's a byte code, and there is a virtual machine inside the kernel that interprets that byte code. Now, this BPF language has been around for a long time. It's 31 years old now. The reason it's been around for a long time, it was initially added to support TCP dump, because TCP dump has, or the implementers of TCP dump had a problem. Yes, we want to filter network traffic because the user wants to trace a network conversation, but the amount of network traffic is huge. So we need a way of filtering that traffic. And one possible way that TCP dump might have done that job is simply to say, put the network interface into promiscuous mode, get all the packets pumped across the kernel user space boundary, and then in user space, inspect the network packet headers. The problem with that kind of approach, which is just theoretical, is that simply the act of pumping all of those bytes across the kernel user space boundary would place a heavy load on the system because there's so much network traffic. And so the idea of BPF was, let's write a program for this virtual, let's have a virtual machine in the kernel, and we write, what I mean by this is TCP dump can construct a program for that virtual machine that gets loaded into the kernel, and the program in the kernel, the BPF program running on the virtual machine in the kernel, inspects network packets to decide which ones are interesting, and whichever ones are interesting, those ones get pumped across the kernel user space boundary. And the whole idea is, of course, that the number of interesting packets is a fraction, a tiny fraction of the total number of packets. So the amount of bytes being pumped across the kernel user space boundary is manageably small. The brilliance of the Seccomp 2 idea was to say, hey, we've already got a virtual machine inside the kernel that has the job of inspecting a bunch of bytes and making some decisions. Those were the bytes in a network packet header. Let's repurpose that virtual machine and instead make it look at the bytes which describe a system call number and the register values associated with that system call number. And so for example, or just by way of history, the Seccomp 2 idea, when it was first proposed, from the time it was first worked on until it was actually merged into the kernel, was about 1 year, which for a major new kernel feature was a remarkably short time. But one of the reasons that kernel developers felt reasonably comfortable with doing this relatively fast was, we're not inventing entirely new technology. We're repurposing this virtual machine that has been in the kernel already for 20 years. We feel very confident that the machine is safe. And so repurposing it, this feels okay. So the idea is we've got a virtual machine in the kernel then. The virtual machine has a few characteristics. It's got a very simple instruction set. It's a small set of instructions. They're all the same size. This means the virtual machine implementation in the kernel is simple, it's fast. There are branch instructions. We can jump in our program, but we can only jump forward. So there can be no loops in BPF programs. This is important because we need to be able to know that every BPF program will eventually finish execution. If there could be a program with a loop, then this could loop infinitely inside the kernel, which of course would be some kind of denial of service attack against the kernel. So the kernel is even able to sort of do various kinds of validation of BPF programs. It knows they'll always complete. It can verify the opcodes and the arguments because the format of the instructions is fairly simple. The kernel can even do things like detecting dead code in a BPF program where there's a jump over a block of code but no jump that jumps into that block of code. If you try and load a BPF program like that into the kernel detects that and actually says, no, here, have an error. You're not allowed to do that. Okay, BPF programs themselves are limited to 4K instructions, which seems to be enough for people's use cases generally. Okay, so There's some features of this virtual machine. It's got a register, a 32-bit register. This is sort of the working area for doing operations. There's a data area. Now, in the context of Seccomp, that data area is bytes that describe the system call. In other words, the system call number and the values that are in the registers that have the arguments. The instructions, as I said, they're a fixed size. They're all 64 bits. They have a certain format. That format, of course, can be expressed as a C structure. The C structure, even defined in a header file, it looks like this. Every instruction consists of a 16-bit opcode. At the end, a 32-bit operand, which depends on the instruction. And for the jump instructions, there's 2 bytes that contain offsets saying how far forward do we want to jump. Okay, an important thing about BPF, there's no concept of state. You can't have a BPF program that executes, saves some result that can then be used later on by another invocation of that BPF program. That's not possible. So for instance, you couldn't write a Seccomp BPF filter that said, I'll do something on the 3rd call to open, something different. There's no concept of state, so you can't do that sort of thing. If you've done some assembler programming, the virtual machine has the kinds of instructions you'd expect to see on a virtual machine. There's load instructions, there's jump instructions, there's arithmetic logic instructions, add, subtract, multiply, divide, left shift, right shift, XOR, and all of the stuff that you might expect. One thing that is sort of particular to BPF is these return instructions. And the return instructions are the instructions that say, terminate execution of the filter, return a result to the kernel with the decision about the system call. Should it be allowed or disallowed? So we've got jump instructions. There are conditional jump instructions. There's also an unconditional jump instruction. The conditional jump instructions, if you've done some assembler programming, none of this is too surprising. There's an opcode saying what kind of test do we want to do. These tests are tests against the value in the accumulator. There's a value we want to test against, compare the accumulator against. And then every jump instruction, this is a little bit unusual in terms of jump instructions, every jump instruction has 2 addresses or 2 offsets. Where should we jump to if the test is true, and where should we jump to if the test result is false? The sort of instructions you expect for conditional jumps: jump equal, jump greater than, jump greater than or equal. There's even a bit set test, are some bits test set. And that's all there is, which at first glance seems like not enough. For instance, what if I did jump not equal test? Well, that's just the false branch from jump equal, just as jump less than or equal is the false branch from jump greater than. Okay, the jump targets are expressed as offsets in the instruction list. An offset of 0 means don't jump. In fact, just do the next instruction. But otherwise, because we've got 1 byte to express the offset, we can jump up to 255 instructions forward. If you want to jump further, there's a jump always instruction, an unconditional jump where the offset is expressed in the operand. And the operand, of course, is 32 bits, which is way bigger than we need to jump as far as a program could be, because a program can only be 4 kilobytes of instructions. Okay, now when the filter gets executed, it gets to examine a data area. The data area is information describing the system call. This is the system call number and the arguments to the system call. The buffer is read-only. So what I'm trying to say there is you can use Seccomp to inspect the system call, but you can't, for example, change the arguments to the system call inside the BPF filter. Of course, that structure can be expressed as a C structure. There's a structure defined in the header files. the structure looks like this, struct seccomp data, and we get a few different fields in there. The first field is the system call number. Which system call are we making? Going down a bit further, the last field is what is expressed as an array, but the point is this field describes the arguments of the system call. On Linux, the greatest number of arguments that any system call has is 6. So there's space here for up to 6 arguments. Now, of course, each system call has a particular number of arguments. It's up to you as the author of the BPF filter to write your filter to look at the right number of arguments if you care about the arguments. We get a few other pieces of information as well. One of those other pieces is the so-called the arch field, which is it contains a number that says what architecture is this BPF filter running on, and I'll explain a little bit later on why that matters. Aside from that, we get another field, the instruction pointer. This is the actual virtual address in your real program from which the system call was made. And when I first saw that, I was quite puzzled. Why is that information there? And I sort of came up with crazy hypotheses about why they have that information there. And then eventually I had a chance to talk to one of the core Seccomp maintainers to say, well, why is that field there? Because we could. There was no particular use case in mind. Okay, now if you're feeling in a 1950s frame of mind, you could write your BPF programs as binary values coded up by hand, but as a first step to making your life easier, the header files do provide some macros that you can use to sort of hand build the instructions that you want to create. And this is doing it the hard way, but I want to do it the hard way so that we actually see what's really going on. And so there's a couple of macros, for instance, BPF statement and BPF jump. And all they're doing, BPF statement, you give it two arguments, an opcode and an operand. Now, for reasons of history that I don't know about, but this goes right back to the 1992 paper that described BPF, the operand is always called K. It's just a piece of notation. But what you can see, of course, is that that macro is really just constructing an initializer. It's constructing an initializer for this struct sock filter structure that we looked at already. And you can see that it's defining the opcode, and at the end the operand, and for the two jump fields it's just putting 0. BPF jump, which is the macro for constructing a jump instruction, we give an opcode, an operand again, and then because the conditional jumps take 2 offsets, we have 2 more arguments, which are the offsets. And again, all the macro is doing is constructing an initializer for this struct sock filter. So some examples. Here we've got a BPF statement. Now it takes a bit of practice to just sort of break this down, but the point is that the macro takes 2 arguments. The comma there is separating the 2 arguments, and the first argument is the opcode, and the opcode is being constructed by just ORing together some bit patterns. These constants are defined in the kernel header file, but the point is these constants are being ORed together to build up an opcode. Now these particular constants, what are they saying? Well, they're saying, first of all, this is a load instruction. Load a value into the accumulator. The next question, of course, is how big a value are we going to load into the accumulator? BPFW says a word, 4 bytes. And then the question, of course, is where are those 4 bytes coming from? And the last piece here, BPF abs, effectively is saying those bytes come from the data area. Okay, and then the question is, well, which bytes in the data area? Which 4 bytes? Well, that's expressed in the operand. And the operand is the value offset of struct seccomp data, arch. Now, when I ask most C programmers if they've ever seen the offset of macro before, the answer is no. But offset of is just a macro. You give it two arguments. One is the name of a structure, and the other is the name of a field in that structure. And it's just giving you back the offset of a particular field relative to the start of that structure. So just going back a moment, there was our struct seccomp data structure, and we're asking about what is the offset of the arch field. Well, the NR field, the system call number field, that's 4 bytes, so offset of arch is the value 4. And that's what this macro is returning. The number, sorry, forward one slide, it's returning the number 4. So we're saying load 4 bytes from the data area, starting at offset 4. And of course, that is the architecture number, those bytes. Some other examples then of instructions. Again here, well this time, sorry, a BPF jump. We've got an opcode. The opcode says BPF jump, it's a jump instruction, jump equal. It's a conditional jump testing on equality in the accumulator. What are we going to compare the accumulator against? BPFK says the value in the operand. What value do we have in the operand? This number here. This is just straight from a kernel header file. It's a certain constant that says, it's the constant that identifies the machine architecture x86-64. Now, if the test is true, we're going to jump forward 1 instruction, which means we skip the very next BPF instruction. Otherwise, we're going to jump forward 0 instructions, which means we will execute the very next instruction. Some other examples. This time a BPF statement here. The opcode says it's a return instruction. We're going to return a value to the kernel. BPFK says the value we're going to return is whatever is expressed in the operand. And the value in the operand is this constant seccomp ret kill process. And this is a value that says to the kernel, hey, kill the process. In other words, the filler has made a decision that we don't like the system call, we dislike it so much that we actually want the kernel to kill the process. Other examples here, another statement this time an arithmetic logic instruction, add a value to the accumulator. The value comes from the operand, BPFK, and the value in the operand is 1. Add 1 to the accumulator. Or, following straight on from that, this time a right shift the accumulator 12 bits. Now, we've got this idea then that each filter, or I'll rephrase that, each time the filter is executed, it returns a value to the kernel, giving a decision to the kernel about what the kernel should do about the particular system call. And the point is that once the filter is installed, every time the process makes a system call, this filter gets executed and it makes a decision. Now, the decision takes the form of a return value, and the return value is a 32-bit value that is in 2 parts. The most significant 2 bytes say what general action should the kernel perform, and the least significant 2 bytes are possibly some value that is associated with the action. Some of the actions have associated values. Examples of the kinds of things that the filter might return to the kernel. Seccomp ret allow. The filter saying to the kernel, yep, the system call is fine, the kernel can just execute that system call. Seccomp ret kill process. The filter is saying, we don't like this system call, we dislike it so much that the kernel should kill the process. If it's a multi-threaded process, all the threads get killed. The process is killed as though by a success signal. There is actually no signal. The process is simply killed. But to something that was observing that process, like a parent process, for example, it would look like the process was killed by a success signal. Another possibility, seccomp ret kill thread. We don't like the system call and we're telling the kernel, kill the thread that made that system call. So it might be a multi-threaded process, but we're saying just kill that thread, which I think in many cases is kind of weird, because we're going to kill one thread and hope that the rest of them hobble along okay. Probably not in many cases. Seccomp ret erno, what we're saying here to the kernel is the kernel should not execute the system call, but instead make it look like the system call was executed and returned an error. And we express the erno value that should be returned for the system call, for the failed system call, in the data component of the return value. There are some other possible return values as well, but I won't try and go into them. Now, if we want to install a BPF program, we use one of these two system calls to do the job. The modern way is to use the Seccomp system call, which has been around for a few years now. The older way is to use PRCTL. I'll focus just on Seccomp. So we say we want to install a filter program. There's a flags argument which can be used to modify the behavior of the system call, but the last argument is a pointer to the filter program that is going to be installed. Now that filter program is a pointer to a structure like this, struct sockfprog, and this is reminding us, by the way, of the networking origins of BPF, a socket filter program. That structure contains two fields. One is the size of the program, and the other one is a pointer to the program, a pointer to an array of struct sock filter elements that are the actual code of the BPF program. I'll back up a second. I'll turn the slides off for a moment. Suppose you're an attacker, and you know a couple of things. One is that people who write privileged programs, things like setuid root programs, sometimes are sloppy. You know this because there's been many examples in the past. People who write setuid root programs, for instance, where they say, oh, I'm going to make this system call, and because I'm super user, it will always succeed because I'm privileged. Okay. Now, you know, and maybe you've even found a program that does exactly that. It makes a system call, but the program doesn't check the return value. And you think as an attacker, great, here's something that I can attack. What I'm going to do is install a Seccomp filter, then run that program, and the filter is going to make that system call fail. And your hypothesis is, as an attacker, okay, the privileged program is going to make that system call fails, but because the program didn't check the return value, it's going to keep going. And of course, that's in a situation that an attacker loves, privileged program in an unexpected place. This is not possible, okay? It's not possible because there is a restriction around the use of Seccomp. Either, to install a BPF filter, either the process must be privileged already, or if you're not privileged, you need to make this call here, a PRCTL call that sets something called the no new privs attribute. And the effect of that attribute is that if the process now executes a privileged program, a setuid program, a setgid program, or a binary that has capabilities, the program won't do the privileged thing. It won't give the process a different ID or give it capabilities. So this sort of removes that pathway for the attacker to try and use Seccomp to compromise a privileged program. If you try and install a BPF filter and you are not privileged and you haven't set that no new privs attribute, the kernel says, here, have an error. Okay, let's look at an example. Now, what this program is going to do, what this BPF program is going to do is filter for open and open@ system calls and kill the process if it tries to make either one of those system calls. So my steps, first of all here, I'm setting the no new privs attribute. Then I install my BPF filter. We'll look at that code in a moment. But then I make a call to open. And of course, the printf statement a bit lower down gives us a clue about what's going to happen. We're not going to get that far because the BPF filter is going to kill the process when it tries to make that system call. Now, here's the function that installs my filter. And primarily it consists of a struct sock filter array, which is the set of my BPF instructions. Now for the moment I'm going to leave some instructions out, but let's go down a bit further. Here's my first instruction that we're going to look at. Load a word from the data area into the accumulator. Which word am I loading? The word at offset of NR field in the Seccomp data structure. In the Seccomp data structure. In other words, load the system call number into the accumulator. Then I have a BPF jump instruction, a conditional jump. Do a jump on equality. Is the word in the accumulator equal to the system call number for the open system call? This constant here, this is just defined in a header file. Okay, it's the number of the open system call. If it is, if the value in the accumulator is equal to the open system call number, I'm going to jump forward 2 instructions. Now that means 0, 1, 2. I'm going to land here, where the filter returns to the kernel saying, kill the process. Now, if the system call number was not equal to the open system call number, I'm going to jump forward 0 instructions, which means I will land here, where I do another conditional jump, where I ask, is the word in the accumulator equal to the open at system call number? And if it is, then I'm going to jump forward 1 instruction, which of course will bring me back down here again, to kill the process. If the system call number is not the open at system call number, then I'm going to jump forward 0 instructions, which will bring me here, which says allow the system call. So every other system call is allowed. The rest of that function, well, here I'm initializing that structure which sort of specifies the filter program, and then I make the seccomp call to actually install the filter into the kernel. Now, if I run the program, let's just do it in practice. First of all, I'll touch the file that the program is supposed to open, which was that path name there, temp-a. And then if I say seccomp deny open, then what happened was the program tried to make the open system call. The filter got invoked. The filter said to the kernel, seccomp ret kill process. The kernel then killed the process as though with a success signal. And the shell said, oh, it looks like my child was killed by a success signal. And it printed out the standard textual description of that signal, which is the string bad system call. Okay, we can be a bit more sophisticated than our examples. This time, a filter based not just on the system call numbers, but actually the system call arguments, or in this case, 1 argument. So I'm going to again do filtering for open and open at. Both of these system calls, which are both about opening files, they both have a flags argument. The flags argument does the same thing for both system calls. And I'm going to be looking for a couple of different flags. Create, in other words, if I'm trying to create a file, I want to kill the process if it tries to create a file. If the process tries to open a file for reading or writing, then I'm simply going to make the call fail with the error e not sup. Now, aside from that, the only other thing we need to know is that the flags argument is in a It's a different argument for the two system calls. For open, it's the second argument. For open at, it's the third argument. But other than that, the flags argument is the same for the two calls. Whoops, I jumped too far there. Okay. Now, what I'm first of all doing, again, I've left out some code, this architecture checking code, but the first argument, or first instruction that I'm interested in looking at, the system call number, I'm loading here a word from the data area into the accumulator. It's the system call number. And then I do an equality check. Is the word in the accumulator equal to the open system call number? If it is, I'm going to jump forward 0 instructions. If it's not, I'm going to jump forward 2 instructions, which will take me, here's 0, 1. It'll take me on to the next slide. Okay, but if this is an open system call, then what I'm going to do is another load instruction. Load a word into the accumulator from the data area. Which word? The word at offset of args1 in the Seccomp data field, in the Seccomp data structure, I should say. Of course, that's the second argument of the open call, the flags argument. So I'm loading the flags argument into the accumulator. And then I just do an unconditional jump, saying jump forward 3 instructions. So that's going to take me further into the next slide. Now, remember, if the system call was not open, I jumped forward 2 instructions, which means I'm going to land here. And there you see I do another conditional jump. I'm asking, is the word in the accumulator, remember the word in the accumulator at the moment is the system call number, is it equal to the open at system call? If it is, I'm going to jump forward 1 instruction, which means I'll land down here where I say load a different word into the accumulator. Which word am I loading? Offset of struct seccomp data args2. Third argument of the system call, again the flags argument. Now remember if I had the open call, I jumped forward 3 instructions. That's actually going to jump me right past these 3 instructions onto the next page. And when I get to this instruction here with the open at processing, of course, also the next instruction is on the next slide. Now, if the system call number was not open at, I'm going to jump forward 0 instructions where I say every other system call is allowed. Now, whether we had open or open at, either way, we end up at the first instruction on this slide. What am I doing now? This time it's a conditional jump with a bit set test. I'm asking in the accumulator, remember in the accumulator by now I have the flags argument, is the ocreat bit set? If it is, jump forward 0 instructions where I say return control to the kernel, kill the process. If the creat bit is not set, then I'm going to say jump forward 1 instruction, which of course brings me here where I have another bit set test, where I ask, is the word in the accumulator, is either the O write only bit set or the O read write bit set? If that's the case, I'm going to jump forward 0 instructions, where again I have a return instruction that says return control to the kernel, this time saying seccomp ret erno. This is telling the kernel, don't execute the system call, but make it look like the system call had been executed and failed, and return an error. And the error I'm expressing in the bottom bytes of the return value is E not sup, operation not supported. And then if neither of those bits was specified in the flags argument, I'm going to jump forward 1 instruction, which means I would land down here. Any other kind of open call is allowed. Any kind of other kind of open or open at call is allowed. Now, then in my main program, things look like this. I set the no new pres attribute, I install the filter, and then got a series of open calls. First of all, an open for reading, an open for writing, an open for reading or writing, or reading and writing, I should say, and then an open with the O creat flag. Now, when I run the program, and I run the program, what happened was the first open succeeded, the second open failed, and my program printed out the corresponding error message, which was operation not supported. That was the open with writing only. The open with O read write, same thing happened. The fourth call to open specified O create, and the BPF filter told the kernel, kill the process. And again, the shell said, oh, looks like my child was killed with a sig-sys signal. Okay. Now, I've missed out one or two important pieces so far. And the piece that's important that I've missed out is checking the architecture. Now, this should normally, opinions differ, but this should normally be the first step in every BPF program. Why is this necessary? System call numbers are different on different architectures. I mean, Linux runs on many different hardware architectures, and on those different architectures, some system calls have different numbers. Just an unfortunate result of history. And that means that if you write a BPF filter that filters on certain system call numbers for a certain architecture, and you happen to try and use that filter in a program that was running on a different architecture, it would potentially make wrong decisions because the system call numbers are different. So the very first thing that you should do, and there's a couple of reasons why this might happen. For instance, you generated the BPF blob in advance, you stored it in your configuration management system, and it was a blob for, say, x86-64, but you had a mistake in your configuration management system, and at runtime you happened to try and use this on an ARM system, loaded that blob into the ARM program as the BPF filter for that ARM program, and of course the filter makes the wrong decisions because the system call numbers are different. You might say, well, I would never be stupid enough to do that. You might be right. You might be right. Okay, there's something else though that matters. There are some pieces of hardware, in fact, they're even very frequent these days, some pieces of architecture, some pieces of hardware that support multiple system call ABIs. Notable is x86, which supports 3 different ABIs, modern x86-64, ancient i386, the old 32-bit stuff, and a funny architecture that sort of sits in between, which was invented by the Linux kernel developers about 10 years ago. And each one of these different architectures potentially has different system call numbers. Now, and the same thing can happen with ARM64, for example. ARM64 has a backwards compatibility emulation mode for 32-bit ARM instructions. And for each of these different sort of hardware type combinations, there are different system call numbers. Okay, now there's some details there, but I won't try and go into the details. My point though is this: when you install a filter for a process, a BPF filter for a process, the lifetime of that filter is the lifetime of the process. You can't remove the filter by design. But during its life, a process might execute different programs using execve if the filter allows calls to execve. And the program might start off executing, I misspoke there. The process might start off executing, let's say, a 64-bit program, but then at a certain point it does an execve where it loads a 32-bit program into the address space instead. And of course, the system call numbers are different on 32-bit. And then, therefore, the decisions the filter would make don't correspond to the system call numbers that the program is actually using. Okay, now, this is what, for example, the architecture check would look like on x86-64. We've got here, first of all, a load instruction that says load the architecture into the accumulator and then do a check is the word in the accumulator equal to the value audit arch x86-64? Are we running on an x8? Are we actually running on an x86-64 system? If we are, we're going to jump forward 0 instructions, but if we're not, we're going to jump forward 2 instructions, which brings us here where we simply say kill the process. We're not running on the architecture we expected with this filter. Don't try and get clever, simply kill the process. But if we are on x86-64, then the next step I do is to load the system call number into the accumulator, and then I do another check. Now the reason for this check, going back a slide, I mentioned there's a few different x86 architectures on Linux, and in particular there is the modern x86-64, but there's another funny thing called x32, and x32 is an architecture that uses the same 64-bit instructions, but it uses 4-byte pointers and 4-byte longs. And because of that, it has to, even though it's using 64-bit instructions, the system calls are different because the size of the arguments is different. So necessarily the system call numbers are different. The thing that distinguishes the 64-bit system calls from these x32 system calls is that in the x32 system calls, bit 30 is set. And so I'm going to do one more step in this architecture check where I say, is the system call number greater than or equal to the constant with bit 30? So you can see there that constant x32 syscall bit there, it's just bit 30. So I'm saying if the system call number is greater than or equal to that value, this means it's one of these x32 system calls. And there, if that's the case, again, what I do is jump forward 0 instructions and kill the process. You might have had enough of the 1960s by now. Okay, it's not a fun way to code up your BPF programs if you're going to write a BPF program of any sort of complexity. So you probably want some sort of productivity aid instead. And there are a few productivity aids. The tool of choice for many years now has been a library called libseccomp. You see, that was first released in 2012, same year that Seccomp 2 came out. Someone pretty smartly worked out, hey, doing this stuff by hand is painful. Let's automate it. And the whole point is it's a kind of library API, and it generates code for you, BPF code for you. It means you don't have to do things like counting instruction offsets. The library will even do things like generating the architecture check for you. It's generated code, so you don't have full control over the shape of the generated code, but you can do things like saying, well, I want a check that does this, and this should be done high priority. In other words, early in the generated code. There's a full set of documentation. I had nothing to do with this. There's a full set of documentation, manual pages, all with examples. It's almost like the developer of the library wanted people to use the library. Okay, but to give you an idea of what one of these, a program that uses these APIs looks like, here the core concept of Seccomp is this, a Seccomp filter context. Basically, it's the hook on which you hang your list of requests for rules, and you initialize it. In this case, I've said initialize it with the default rule that system calls are allowed. So everything that is not explicitly treated is allowed. But then I add a couple of rules here where I say, give me a rule for the clone system call which makes the clone system call fail with the error eperm. Give me another rule for the fork system call that makes the fork system call fail with the error e not sup. Then I say, generate the code and load it into the kernel. And this installs the filter, generates the filter and installs it into the kernel. And from that point on, the system calls that the process makes are going to be checked by the filter. At this point, I don't need the filter context anymore. It's consuming some memory, so I free that memory. That's what that API does. And then I make a call to fork. And of course, the filter at that point is going to cause the system call to fail. If I run that program, something slightly surprising happens. Yes, the fork call does fail. It fails with the error operation not permitted. Now let me go back just a moment. The error for fork was supposed to be E not sup, operation not supported, but instead I see the error EPERM, operation permission. Oh, sorry, I've misspoken. Operation not supported and operation not permitted. The reason is that the fork wrapper function in glibc underneath actually calls clone. Okay, now there are some other tools as well out there. There's a thing that's appeared in recent times called Easy Seccomp. It's a DSL type arrangement, a domain-specific language for writing your Seccomp filters. It came out just over a year ago. I'm not sure what the state of that project is. There's not a lot of commits in the project lately, but it seems to be an idea that's worth watching. Maybe they feel like they've already got the working tool they need and they're not doing further development. There's a BPF compiler. This lets you write your BPF filters in a kind of assembler-like notation, but you can use things like labels, so you don't have to count offsets in your assembler code. Okay, I knew I need now. I'll just jump forward a little bit. Now the point is that when you install a BPF filter, every system call that the process then makes is going to be checked by the filter. There obviously must be some cost to this, but you're prepared to pay the cost because you want this sort of security guarantee. Just an example of a program that I have in source code. The source code is all available on my website. A program that installs a BPF filter that executes 6 instructions for every system call, 6 BPF instructions. And the program, what it does is in the main loop, it tightly loops calling the get PPID system call, which is a really simple system call. If I install the filter and then do that loop, the program is about 20% slower, okay, than it would otherwise have been. Assuming the JIT compiler is enabled, which it is by default nowadays. In fact, it's immutably enabled by default nowadays. There is a JIT compiler for BPF in the kernel that converts the BPF bytecode into native code so it executes faster. This seems expensive, but there's a couple of things to remember. Get PPID is a cheap system call, so the relative cost looks great, but also programs don't spend all their time making system calls. My program's very artificial. It's trying to make system calls constantly, so it seems expensive. If you want to do, I won't say more on this slide, but if you want to do your own experiments in terms of measuring the cost of BPF filters, I've even written a small program that you can just use to sort of do some measurement experiments. I think really then I just want to finish off with some caveats. One of the problems that you have with writing a BPF filter is, okay, I want to filter my program to say, you know, these system calls are allowed, the other system calls are disallowed, but actually which system calls does my program make? How do I know what my filter should allow and disallow? This is not an easy question to answer. There are ways that you might try and work this out, but they're not necessarily foolproof. And what if you write a filter where you get it wrong? In other words, you did a lot of testing of your code with the BPF filter, you found that everything worked fine, but then one day in production, your code took a path less traveled and executed the system call that you didn't know about. And the BPF filter kicked in and said, no, sorry, kill the process. Okay, you've successfully used the BPF filter to inject a bug into your application. It's a risk. Now, filtering is based on system call numbers, but applications don't invoke system calls directly. They invoke them using wrapper functions in the C library. And this has a few implications. For instance, some wrapper functions underneath call a system call of a different name, like fork wrapper function calls clone underneath. You need to know that sort of thing if you're writing filters, potentially. The manual pages help, by the way. glibc behavior changes over time. Once upon a time, the open wrapper function in glibc called the open system call, but at a certain point, they switched over to calling open@ underneath. If you're going to do filtering for a certain kind of system call, you want to probably filter for all of the related system calls and treat them all the same. There's a few different ways that you can open a file, for example. So what I'm really trying to say there is, BPF code, it's just like any other piece of code. It's not something you create once and then forget about. It's just like any other piece of code. You need unit tests. You probably need continuous integration testing. When you're going to migrate to a new operating system environment, new platform, you need to have all of that testing in place also for your BPF filters. And I don't want to suggest at all that that is easy. Of course, it is hard. The last link there is sort of a war story of someone who tried to do all of this and then gave up because it was just too hard. But it was one person working on their own, trying to do something that was quite ambitious. But, it's not easy. Okay, now this is just a slide here with some places where you might go for some further information. But other than that, I am done. There's not really time for questions, but who knows? Maybe there's a quick question. Eric.
Yeah, you said that the BPF program is connected and the Seccomp programs are connected to the process.
Yes.
Is it inherited by shipper?
It's a good question. Are Seccomp filters inherited by child processes? And I'll back up a second because you said, Seccomp filters, are they connected to the process? More precisely, filters are per thread. But the point is that if you do create a child process using fork, the child process inherits the filters. So you can't use fork, for example, to escape filtering. Other questions? Okay, thank you very much.